11. Today we're looking at the exercise 4B on the truncus on page 150 of your textbook. Last lesson we looked at the idea of the rectangular hyperbola, which is defined by its key feature being that it's, for example, 1 over x, and the idea that it's got an asymptote, or rather two asymptotes, where one allocates one direction. So for example, we've got the red line symbolizing a hyperbola, where we've got the lines almost reaching but not exactly reaching the asymptotes there. So it's defined by it being the opposite. Now you might remember quadrants back when we did trigonometry in previous years, but we'll just keep in mind that it's an opposite sides. So that's a rectangular hyperbola. But if we try to apply and use a squared function and apply that inside of our rectangular hyperbola, we actually end up with a truncus. If I have the example of, let's say, y equals 2, instead of writing 1 over x, I write 1 over x squared. Now, it's not the entirety of it squared, but I'm saying just 1 over x squared. We end up with something quite similar, but still somewhat different. So let's go ahead and actually fill in this table. I'm going to substitute any x value into my y and into my function in order to get y. So for example, if I substitute x as 0, so instead of writing x, I write 0 here, we will end up with, well, undefined. So I'm going to write undefined here. If I substitute x equals to 1, we end up with 1 over 1, which is 1. If I substitute x equals to 2, that's 1 over 2 squared, which gives me 1 over 4. And you see a trend. 1 over 3 squared gives me 1 over 9. Let's go the other way, go into the negatives. 1 over negative 1 all squared. So that's 1 over negative 1 squared like that. And we end up with 1 over 1, which gives us a value of, you guessed it, 1. I do the same thing. I substitute negative 2 into it and end up with 1 over 4 and 1 over 9. You'll notice that what's happening is that as we get further away from the asymptote at x equals 0. So imagine if I drew a line right here, where that is symbolized by x equals 0. As I get further away from x equals 0 and get further, let's say in the more positive direction, the value actually decreases from 1 to a quarter to 1 over 9 to 1 over 16, etc. Now it'll never reach where y equals 0. Because remember, no matter what value I put for the denominator, it could be 1 over a million squared. It's still not going to give us 0. And so what happens is we end up with another asymptote on the bottom, along the bottom here. Imagine that's a perfectly straight line, and we end up with y equals to 0 as another asymptote. I'm going to go ahead and plug these points in. I have 1, and then a quarter, and a ninth. You get the idea. As we get further away from our, no, that's probably not the best line, but as we get further away from our x equals 0, we end up with a value of y that gets closer and closer to 0, though never actually reaching 0. And as you can imagine, as I get closer to the asymptote, where x equals 0, as I go in this direction, our value of y increases at an astonishing rate. If I was to substitute 1 over, let's say, 0.5 squared, that would give me, well, 1 over 0.25, which would give me 4. And if I keep making that value of x smaller and smaller, we'd end up with a y value that increases at an exponential rate. If I do the opposite, you'll notice the same thing. It's symmetrical across that asymptote. So we end up with the truncus. Now it's called a truncus. The way I like to remember is that a truncus, it looks like a trunk. So imagine if I've got the leaves there, it looks like a trunk. Now the actual transformations are identical to that of the rectangular hyperbola, and in turn similar to that of parabolas. So the same thing, and I'm going to put this into practice into an example that's quite difficult right off the bat. We've got y equals to 1 over 2 times x plus 3 squared minus 4. Now the first thing some of you might think is to expand the brackets. We don't expand the brackets. It's already in this form here, where we have some number over x minus h squared plus k. Now what you could do is you could write it as y equals to a half times by 1 over x plus 3 squared minus 4. Now that inherently is the same. It is mathematically the same thing. If I was to multiply it out, it would be the same thing. However, we're going to focus on this aspect here. The reason being is because the asymptotes aren't affected by dilation. I could have a value of 100 here, and my asymptotes don't change. For the reason being that, well, well, if my x equals to, let's say my asymptote was here, if it's dilated this way, it's still going to be the same thing. My asymptote is still going to be at that value of x equals to 3. If my y value, let's say, is this over here, where y equals to 2, if it's dilated, it doesn't really affect it because it's a translation that's affecting it. So in our situation, we've got a minus 4 at the end here, a minus 4. So I know that my asymptote, or my horizontal asymptote, of y equals to 0 goes down to y equals to negative 4. Now you can write this out as translation down, 4 units down, but I'm just going to write it as this. My asymptote, that's my horizontal, so my vertical asymptote, where before it was x equals 0, which is this line up here, it's going to be shifted. Now remember, it's inside the bracket or under the fraction. That's what we're focusing on. It's minus h, so we do the opposite. So instead of saying plus 3, we're going minus 3. We're going x equals to negative 3 because x is shifting 3 units to the left. Now, it's a very odd concept, but the reason we do that is because we're thinking about how do we compensate to get the same value. If I was comparing where it's just x squared versus x plus 3 squared, for whatever value I'm trying to get, I have to take away 3 every time to get the same y value. That won't make sense at first thought, but when you think about it further, it should make more sense. How do I compensate for the value of x in order to get the same y value? With that in mind, I'm going to go ahead and try to draw my function. I know that my line is going to be, I could do better than that. I'm going to go ahead and draw a general Cartesian plane just so we can see. I'll draw in my asymptote, as well, which is y equals to negative 4. Let's go ahead and fill that in here. And my other asymptote is going to be at x equals to negative 3. So I'm just approximating my sketch here, and we'll end up with our answer. Alright, so that's x equals to negative 3, and that's y equals to negative 4. There is no negative, there is no reflection, therefore, and I'm just going to go ahead and draw my function. I know that it's going to be up here, and it's going to go through these points here, and the same thing occurs on this end here. And that's my function. It's a truncus. We have no reflection, so there obviously is no need to flip it. And we have our asymptotes there. If you would like, you're more than welcome to actually substitute the values in. For example, if I try to find my x-intercepts, x-intercept, I let y equal to 0, and you have 0 equals to 1 over 2 bracket x plus 3 squared minus 4. I'm going to add 4 on both sides. We end up with 4 equals to 1 over 2 times x plus 3 squared. I'm going to multiply both sides by 2. I end up with 8 equals to 1 over x plus 3 squared. I'm going to multiply it on both sides. So 8 bracket x plus 3 squared equals to 1. I'm going to divide by 8 on both sides. It's a long process. X plus 3 squared gives me 1 over 8. I'm going to square root both sides. I get x plus 3 equals to 1 over 8 square rooted. Oops. There we go. Square root there. And then I can get x equals 1 over root 8 minus 3. Now remember, because we square rooted, it's plus or minus. Now, it's a long process. This is typically something you can do in the calculator, or sometimes when you presented this in an exam 1 question, for example, where you can't use a calculator, it would be nice, easy numbers. But the idea is that you should be able to get the same number of solutions as you do in your graph. So that's the truncus. Please let me know if you have any questions. It's pretty much identical to the rectangular hyperbola, just with them being symmetrical. Best of luck.